code. And previously, so this is based on expander graphs, and previously either these algorithms for generating this were impractical, or they didn't have a good linear distance except with a negligible probability. And the second is that they use a proof composition technique using code switching. So it's based on tensor code polynomial commitment schemes. So yeah, this line of work with so BCG and then going to breakdown. And the idea is that you take a polynomial commitment scheme that's designed to achieve a square root verified time and proof size, and then you add an outer proof to this. But the nice thing is that you don't need to prove any hash functions or the like in this outer proof, but you can instead use this, these hash functions stay outside. So what we did is we show that in fact Orion, as presented there, is unsound, and this is both with and without zero knowledge. And we in fact demonstrate this can be broken efficiently with practical attack. And then we also propose a solution, and the solution preserves the linear time, the linear proofer time, and it also doesn't add any disadvantages. So it doesn't add any hash functions inside this outer snark circuit, and it also doesn't add any new rounds or any new commitments to the protocol. And then for zero knowledge, what we need to do is we need to switch to a different zero knowledge scheme, and this has some trade-offs. So the proofer time increases somewhat, but then we gain the fact that the verified time and the proof size actually improves quite a bit. So how does this polynomial commitment scheme work? So first, the commitment phase is we have a so yeah, it works for both univariate and multivariate polynomials, but let's look at a univariate polynomial. So we have the coefficients here, and we put it into a matrix, and for simplicity, let's assume this is a square matrix. And what we do is we encode every row of this matrix using a linear code. And note that this matrix we can multiply by both sides with special designed vectors so that we can evaluate. So here we have, so on the right we have all powers of x up to k minus 1, and then on the left-hand side we have multiples of x to the k. And then k is equal to the square root of the size of the matrix. So to commit, we take the rows of this matrix and we encode every row, and for zero knowledge we add a random vector and then also append it to the right. And what we then do, what is not done in breakdown, is we also encode every column of this matrix using a linear code. And that's the commitment phase. So then we use a Merkle commitment on this resulting matrix, and then this is the resulting polynomial commitment scheme, polynomial commitment. So then the evaluation phase works as follows. So breakdown works by taking a random combination of these rows. So every row is this encoding, and then we take a random linear combination. So we take an inner product with gamma with these rows, and then the verifier checks two things, namely that the result is still a code word, which should hold if it's a linear code, and then secondly, it checks that this linear combination is well formed. And so both of these steps take time squared of n. So it's the verifier just encodes this w gamma and this random vector, and then also add some random columns. Yeah, these columns are also size squared of n, so this takes time squared of n. And for the evaluation phase, we do the same, except we don't use a random vector, but we use instead a this x vector that I showed earlier. And Orion then, on top of this, adds an outer snark. So what the prover does is it commits to this linear combination. Then this code is built inside the snark, and then instead of checking this code entirely. The verifier only checks at some random points. And secondly, the verifier also samples a random row set, and then this thing that we have here, this linear combination at these random columns, the verifier only checks at these rows, compared with at the commitments that we have to the polynomial commitment scheme. So this is the entire procedure that we have. So the verifier sends a challenge vector, the prover computes this linear combination and sends a commitment to this linear combination. Then the verifier sends a column set, and for zero knowledge we need that the verifier doesn't send j as well as j plus n, because then they can subtract away this randomness. Then the prover commits to the CP snark witness. Then the verifier sends this row set, and then the prover computes the CP snark proof. So yeah, it's a commit and proof outer snark. So that's what's happening here. So the prover can first commit to this, and then later use this commitment inside the snark proof. So yeah, then here the proof checks this. Checks that it's indeed a valid code word. Then the commitment, this linear combination, is checked with the columns that the prover has already committed to here. And then finally, these columns are encoded, and this is compared to the original polynomial commitment. So then maybe you have seen the issue here. So it's in these 4 steps. So the prover first sends a commitment to this random linear combination. Then the verifier sends a column set where they make sure that this condition holds. Then the prover commits to the CP snark witness, and then in the CP snark witness, this code is checked. But this means that the prover can choose R gamma after the column set has been chosen by the verifier. So the prover already knows at which columns this condition will be checked. And another issue is that the encoding and the randomness are never checked at the same offset. So to satisfy this condition, the prover can just pick any R that satisfies it, and the rest they know will never be checked. So yeah, then you might think maybe it's this condition that's in fact the issue. So yeah, we can evaluate to any point, but this is not in fact the case. So even if we remove the zero knowledge, then this condition that we have reduces to just the check that that the encoding of the random linear combination of the witness matches the commitment, and but we still have the same issue. So the column set J is known before the witness, before this W gamma is selected by the prover, and so the prover just has to solve this linear system here. So it's an encoding of this of W gamma, and it should be equal to the commitment at columns J. And the columns J are known by the prover at the point where they can still choose this W gamma. So it's solving a linear system, and it turns out that this system has a solution, except with negligible probability. So it's basically always the prover can cheat. So then the question is how to fix. So really, what is the issue? We have to commit to W gamma and R gamma before we know J. But at the same time, we want to commit to these columns D inside the CP snark, but at this point we want to know J because we don't want to commit to the entire witness in the CP snark, because then we won't have succinctness anymore. And we want a linear prover, and we don't want to assume that the outer snark has a linear prover, because if it did, then we might as well use the outer snark in the first place. So one solution is to split these two. So first commit to this, and then commit to that. So yeah, we could simply add another round of commitments, and basically we have two options. We could just have a general commitment and then open this commitment in the outer snark. The disadvantage is that now the outer snark circuit grows. Yeah, we might have to compute some hash functions inside the snark. And this means that the proof size increases, and probably also the verifier time and the prover time increases. The different option is, well, we use a CP snark, so maybe we can just add another round to the CP snark. And this is better, but yeah, now we have two succinct commitments to the CP snark, which increases verifier time and proof size. And we could use batching, but then yeah, we don't get around the fact that this increases the proof size. So what we did is we found a solution. So it turns out that this J actually has two purposes which can be separated. So this J that we need to know to check the random linear combinations does not have to be the same J that we later use to check the commitment to this C gamma. So yeah, we use this J to check the linear combination of rows, and then finally we use J prime to compare with the commitment that we have. Then we still have, so how do we add zero knowledge? So if this set, this initial set J has some index J, then this new set cannot have J plus N, because then we still have the same problem that we can subtract and obtain some information about the witness. So yeah, we can then restrict this set again, but then it's still unsound, because the prover now at step 5 in the protocol would know an index that will definitely not be queried by the prover. And this might give the prover some advantage. So this is why we switched to a new zero knowledge code. So what we do is we don't want to impose any restrictions on J and J prime, and we use a polynomial to hide these evaluations of the linear time encodable code. And because these points, these sets where we reveal our constant size, it means that this polynomial that we add can also have a constant degree, so this won't harm the linear time prover. So yeah, it's fixed degree, it doesn't have a constant term, and the nice thing is that this retains the minimum linear distance, and it's a general transformation, so we can use any linear time encodable linear code, and this is what it looks like. So we copy the code word, and then we add this polynomial without a constant term, and the relative distance is the same that the original code has. And then what we do is we also do some more things. So yeah, we need a new zero knowledge proof and a new knowledge soundness proof. So we provide these proofs, and we make sure that it's more rigorous than the original proof was. Now, another issue is that you might have seen that I had a star next to the logarithmic verifier time. That's because the verifier actually needed to produce this random vector gamma, but this vector gamma is of the size squared of n, so that means that the verifier is not logarithmic in a simple way. So instead, there is this work from Diamond and Posen, which uses this tensor product instead for the verifier randomness. So we incorporate this, which means that the verifier is now actually logarithmic. And we also consider multi-point openings, and we also have a consideration of feature mirror in the paper. Okay, and then we arrive at our new CK snark, which we call Scorpius. And so we have now a proof system with a linear proofer time. It's got log n verifier time and proof size. And so compared to Orion, it's got an increased proofer time, but not by too much. And then we have a faster verifier and smaller proof size. And we also now have a rigorous knowledge soundness and zero knowledge proof so that we can have some more confidence in the final proof system. So in conclusion, Orion turns out to be unsound, both if you consider the zero knowledge version and the non-zero knowledge version. We provide a new zero knowledge code which might be able to be used in different systems as well. It's a general transformation that retains the minimum relative distance, and it's a linear time, or it's compatible with the linear time encodable codes. We propose Scorpius, which is an alternative which solves the issues with Orion while retaining the linear prover and doesn't have any significant disadvantages that you might expect from like a naive fix. And that's the presentation. Thank you. Are there any questions?
Excellent, thank you. Questions? Okay, so let's thank the speaker again. Yeah, we're a bit early. We have a break now. Okay.